Pre-Calculus 2.2 Day 2 notes. And so we're just continuing looking at polynomial functions. And so we're going to reinforce sketching the graph to start with, and then we're going to find some equations and use Desmos to answer some questions. And so sketch the graph of the polynomial function. And so you're going to want to use the zeros and look at end behavior, just like the last example in the last set of notes. And so I'm going to set this equal to 0. I'm going to look for that common monomial factor that I see, which is 2x squared. And if I divide that out, I get an x minus 3. And so this x squared is really x equals 0 twice. Since it's to that even power, I'm expecting, it's really an x equals 0 twice, 2 zeros. And so I expect there to be a bounce, where it touches the graph and bounces back in the other direction. And then 3 is our other root. So at 0 and at 3, we have zeros. And then just like before, I expect you to show a sign chart and test each interval as to whether it's positive or negative. So start with, what are my intervals? Again, you're looking along the x-axis and starting from negative infinity to that first 0, which would be negative infinity to 0. That's one interval. Then in between those two x-intercepts, which is from 0 to 3, and then beyond. So we're just looking at that x-axis and splitting it up and naming the intervals between the zeros. And then you need a test number in each of those. And so I would, negative infinity, I'd say it as close to 0 as I can. I'd use a -1. 0 to 3, I would just use a +1. But you can pick any number between 0 and 3. You just can't use 0 or 3. And from 3 to infinity, I'm just going to use 4 because I want to keep it smaller if I can. And then I need the sign of that product of 2x squared x minus 3 by thinking if I put a -1 in there, the 2x squared is going to be positive, and I put a -1 with x minus 3, I get -1 minus 3, which is a -4, so that's negative. And when I multiply a positive times a negative, I get a negative. So I expect that in that interval, that the function will be below the x-axis. And then as I test 1, I put 1, 2 times 1 squared is positive. And if I put 1 into x minus 3, I get 1 minus 3 is a -2. That's negative. And again, I get out a negative. So the graph is going to be below in that interval. And then if I put in a 4, I get positive, and then 4 minus 3 is +1. So I get positive times positive, and that product will be positive. And so in that interval, the graph will be above the x-axis. So that's one thing. And then for end behavior, this is a positive leading coefficient with an odd exponent, so I expect it to act like x cubed. So as x goes to negative infinity, y is going to negative infinity as well. And as x goes to positive infinity, y is going to positive infinity. It's overall increasing. So with that, and knowing that I have that x squared, which is a double 0, and I expect a bounce, and that in both of these first two intervals, the graph is below the x-axis, then I'm just going to come up, sketch, bounce back, and go back down. Now I've got to think I'm going to, at 3, I have to change from below to above. So it touches once, so it's going to then go back and then put an arrow that it indicates it's going up. And how far down you go right here can vary from person to person because it's just a sketch. We're not putting in a bunch of points to be more accurate. It's just using end behavior and the intervals using the zeros and the sign chart test to say if the function should be below the x-axis or above the x-axis. And that all of that agrees. So there is sketching the graph using end behavior and zeros, and a sign chart test is expected. All right, so then another set of problems, find a polynomial function that has the given zeros with leading coefficient 1. That's mentioned just so that we all have the same answer. And the idea here is x equaling -2 is a 0. That means that a factor is going to be x plus 2. And that's a factor that if it equals 0, well, it gives you an x-intercept at -2. So a factor is going to be x plus 2. And then a 5, that means x equaling 5. And so a factor from that said it is x minus 5. And we want it to be of degree 2. So if -2 is a root, then x plus 2 is a factor. And if 5 is a root, then x minus 5 is a factor. And so just multiply that out, and my function is going to be f of x is x squared minus 3x minus 10. You need the f of x equals a polynomial function. It has to have a y equals in there. And then the leading coefficient of that is 1, so there's no vertical stretch or anything to that. So there is your answer. So now, this next one, these two are what we call conjugates. Their first term is 3 and the signs are the same, but the plus root 2, minus root 2, those signs are opposite. And so that means you have x equals 0, x equals 3 plus root 2, x equals 3 minus root 2. Those are all solutions. So x is a factor, and x minus 3 minus root 2 is a factor, setting that equal to 0, move it all over. And then x minus 3 plus root 2. If you move that all over to the left side, set it equal to 0. Those are my factors for this function. So you're just subtracting, getting it equal to 0, subtracting, getting that equal to 0, and that gives you your two factors. Now, a special way to multiply these that makes this a lot easier, because you have to multiply these out. So when we say the function, you do not leave it in factored form. It is a given that you're going to multiply these out. But what you do is you regroup so that you have the first two terms in their own set of parentheses. This is going to be an easier way to graph, or to multiply, excuse me. And so then what you're thinking of is that this right here is A, and this right here is B, so this is an A minus B, and that this is an A, and then it's plus B. So A is x minus 3, and B is root 2. And when you multiply A minus B times A plus B, you get A squared minus B squared. So I still have the x out in front, but I can make this an x minus 3 squared minus root 2 squared. And this will be a much faster way to multiply this out. So you're just recognizing the first two terms are the same, and the last term is the same, and one's subtraction, one's addition. So it's that special product that becomes just that first term squared minus the last term squared. It just happens that the first term is a binomial. Now, you need to expand this, and the square of a binomial is a trinomial. Let's square it, multiply, and double it. It is x squared, the -3 squared, and in the middle you multiply those two, a minus 3x, and double is a minus 6x. It's just foiling it. And then when you square the square root of 2, you get 2, so you have minus 2. So now I have x times x squared minus 6x plus 7, and finally, as I distribute that, I have an x cubed minus 6x squared plus 7x. And there is my function. I need the f of x equals. Notice how I wrote the equals all the way down. I wrote complete full steps, and that's what you need to do as well. And the leading coefficient of that's 1. So you have to multiply it out all the way to that. All right, so then using a graphing utility, and since we don't have graphing calculators, we're going to just use Desmos. If you have a graphing calculator, I strongly urge you to figure out the zero or root feature. If you move on to calculus, you'll need to do that with your graphing calculator, not just on Desmos. But use the zero or root feature to approximate the real zeros of the function. Then determine whether the multiplicity of each zero is even or odd. And so we'll talk about that after we look at the graph. So we're just going to go to Desmos and graph this. So I'm going to go to here and I'm going to add desmos.com, graphing calculator, pick that one, except for I didn't want it to do that. So clear that one and reset. I just hit the home button and it kind of put it -10 to 10. And then I'm going to type in, and for f of x equals, you need just y equals. It doesn't do that function notation. And for the 1/5, if you just do 1 divided by 5, it'll put it in a fraction. If you keep typing, it'll put it in the denominator. So if you hit the right arrow underneath the function, underneath the graph, it'll move the cursor so it's out of the fraction. And then you have a left parenthesis, x plus 1 right parenthesis. And if you hit that a squared button, it will put the square on it. Then I have another left parenthesis, and we have x minus 3, and then a right parenthesis, and then a left parenthesis, the 2x minus 9, and a right parenthesis. And then you want to just adjust this, and this one I think I can just do kind of a finger pinch and get it in there. And there we have it. Now, what we are supposed to be looking at is looking at the zeros in the graph of these, the roots. And so on Desmos, it's pretty easy because you just hover over it, and it will give you the points of the x-intercepts, and those are what we're interested in, and the nature of that graph. And so at -1, that's going to be at the root of x equals -1, and then 3 and 4.5. The roots are -1, 3, and 4.5. And at -1, because the graph bounces, that's of an even. It's an even root because it bounces. So when you have an even root, the graph comes and just touches and goes back in the same direction. We've been calling that a bounce. An odd root is at 3 and at 4.5, and on odd roots, the graph passes through and changes from positive, negative, or negative to positive. It doesn't bounce and go in the same direction. So at odd roots, 3 and 4.5, the graph just passes through. So -1 is going to be even because you have a bounce. 3 and 4.5 are going to be odd roots because the graph passes through and changes from positive to negative or negative to positive. And so that's the roots of that. And so then we're going to grab that and sketch that in the problem, just having used Desmos. So I'm going to go back to Notability and use a zero or roots. And so I had pre-scanned that. And so I am going to take this, I think, and copy and move it up here. Otherwise, you can just hand sketch it. Oops. I thought I could just copy it. Paste. There we go. And move it in. And of course, I need to get rid of that dot in there because I don't want it. It's being finicky here. Just want to move it over a little bit. All right. So anyway, so use a zero or root feature. So in Desmos, you just tap on it or hover over it to get them. There are other processes on graphing calculators, and you can put in your graphing calculator model and learn how to use your graphing calculator to find zeros and roots. And then determine, so the roots are the zeros or roots are -1, 3, and that 4.5 or 9/2. Those are the zeros or the roots. And then -1, the 0 is even because we have the bounce. And 3 and 4.5 are odd because the graph passes through at those. And notice, yes, it does have to do with the exponent being odd or the exponent on that root being even. So just, it's how many times the root is repeated, and if it's repeated an even number of times, you're going to always have a bounce. If that factor is repeated an odd number of times, to the first, to the third, to the seventh, the graph will pass through at those zeros or roots. All right, so then this next question is something that you see often in a maximizing, minimizing kind of problem, where you have a square piece of paper. Okay, this is my square piece of paper, and basically you're cutting out corners of length x, but you're starting in this case with a length of 24. And so then as you fold that up, so you cut out the corners and you fold it up, and it creates this box. And so then as you create the box, so this was 24, but you cut off x here and you cut off x here, so the length from here to here is 24 minus 2x. Same thing from the length from here to here. This is going to be 24 minus 2x because you've cut off this length of x and you've cut off this length of x. So you get a box that when you fold it up, oops, there's my box. When you fold it up, its height is x, and this side is 24, but remember you cut off x on both sides, so take off 2 lengths of x, and you did on the other side as well. And so as you cut those up and you fold it up, you get this. These are the dimensions. So in part A, when it says write the function v that represents the volume, well, volume is length times width times height. So v of x is x times 24 minus 2x, 24 minus 2x. And there is your answer to A. That is a function, so you need the v of x equals the volume of the box, and just leave it in factored form. Now, in part B, the domain is kind of interesting, because if you take that box and you start taking bigger chunks of x out from both sides, then this length of 24, this length of x that you're cutting out is getting to the point where it would almost meet up. And you can't cut more than halfway, half of that length or width, without cutting into the other spot. Anyway, you can only get half of 24. And you can't actually, if you made x 12, you would end up cutting the piece of paper in half, or the cardboard in half, and that won't work at all. So your domain on this type of problem is half of whatever your smallest dimension is. So a different example would be, what if you started with an 8 by 10 and you cut out corners of x? Your smaller dimension would determine and drive your domain. And 8 divided by 2 is 4, so you can't actually let x be as large as 4, or you would cut this side in half. And so your domain on this would be 0 to 4, not inclusive, using interval notation. So back up to this one, since your lengths on both sides are 24, your domain is 0 to 12. Not inclusive, they have to be open. You can't have a length, you can't cut out 0 and make a box, and you can't cut out 12, because if you do that, then you'll cut the whole piece of paper in half, or box in half, and you won't be able to create the box and fold anything up. So that is the domain. And as a sketch a graph of the function, estimate the value of x for which the volume is a maximum. And so In part C, if I set it equal to 0, my zeros are 0, and if I solve 24 minus 2x equals 0, get 24 equals 2x, my other 0 is 12. So I have zeros at 0 and 12. And that is my domain. And if I thought about this volume, I would get an x, a negative 2x, and another negative 2x for my leading term. That would be, as I multiply things out, if I expanded this, the largest and leading term would end up being 4x cubed, which means you can have up to 2 turning points, one less than the degree, and that the end behavior, it would start by decreasing and increasing. So the graph of this is going to come, and then at 12, 12 is a repeated factor. It's of degree 2. It's repeated twice. So it's going to act as an even root, meaning that the graph is going to come, touch, and go back in the same direction. So knowing a little bit about the end behavior, kind of estimating if I expand that volume, what that leading term would look like, it looks something like this. And so I want to figure out, what is that height? What is that maximum volume? And that's what I'm going to be looking for in Desmos. And really the graph to the left and to the right doesn't really matter, because the domain is just 0 to 12. But yet we can look at the overall shape that we expect using end behavior to kind of help us figure out what's happening there. So anyways, we need to go to Desmos and graph this. And this one's a little trickier when you go to Desmos. And so if I go here and I X out of that and I start putting in, so Y equals, and we've got X, and then 24 minus 2x, right parenthesis, left parenthesis, 24 minus 2x, right parenthesis. It's like, what's going on? Well, it kind of adjusted to 12 right there for me. So I see 0 to 12, but it looks like it's almost on the y-axis. It's because this is getting to be a very large number, so I need to pinch and pinch and pinch until I can kind of see, what's happening. And so that's where it really helps to kind of know end behavior. And I can kind of see that in that 1,000, as I look, that it's peaking out. It's peaking kind of at that. So now I'm thinking, okay, my x values are 0 to 12, and as I kind of searched and had to play with Desmos to kind of see what height it's going to, which is over 1,000, there's a toolbox up in the upper right-hand corner. It's got the above the plus. It's a tool. If I hit that, I can actually go to my x-axis and say, okay, I'm going to just go from -2, and I'm going to go to 15. So it's a little to the left and a little to the right of my actual domain, 0 to 12. And my y-axis, I need to get all the way up to 1,000. So I could say -25, and then I think that's going to give me -25. I don't know what that's going to give me. I'm going to go -25. Try that again. 24. That's okay. 25. And then I need to get up to over 1,000, so maybe 1,100, and do the step by 100 or something. And then, yeah, I think that looks good. So I'm going to go ahead and just tap out, and then it's kind of there. I can pinch a little bit, and I can move, or, you can adjust. So you kind of have to search it a little bit. It's not just intuitive, so because that volume gets large. And so you need to look at a table of values or start putting numbers in. And now on Desmos, you can just tap the zeros and they give you the values. Well, the same thing for that maximum, and it actually gives you the maximum. Now your X is the length of the squares, and I believe that's in inches that you need to cut. So cut out 4-inch squares on each corner, and the volume is 1,024, and for volume that would be inches cubed. So then sketch that graph and put that back into the problem using your graphing utility. So this right here can just be 4, 1024. And so that's at 4, and then at 8, And, so say this down here is at 1,000 kind of thing. And then answer the question for part C, sketch a graph and estimate the value of x for which the volume is the maximum. And in this case, we had Desmos give it to us. So when x is equal to 4 inches, then the maximum volume. And if it was an estimate, you just say, then the approximate, x value is 4 and the maximum is approximately this. The maximum value is 1,024 inches cubed. So using Desmos, using some things about end behavior to help us get the shape of it, help us search for it, and just this is a typical problem that you see that students should know in pre-calculus.